有挺多的，加起来应该有20多个吧，不算多，不算多。就是 conformal prediction， 讲那个不确定变化 conformal prediction， 就是有一年的那个 ICML 的最佳论文的相关。
它有你 conformal prediction， 做那个
calibration， 你们做 calibration？ 我们就是这个有一个集合，就叫 calibration 集。
calibration 赛就是我们用来做 calibration 的。
其实我只是去做，它是跟 training 集合是高度相当嘛，但是不一样的。
你是直接去，就是你是不是一个 post hoc 的 method， 你是直接就是用一个顺的一个 conformal 的一个 model。
不是，我们是这个 model 是训练好的，但是训的过程中的一些东西，一些 information 会给到那个 conformal prediction。我们下一步会像你说的，就是把那个 conformal prediction 塞到那个 training 过程中。
那了解这个。
The same stuff as certification, you can compare. It's not super interesting, it just works similar. This is what we expected, so this is also not super surprising, it's more of a proof of concept. Yeah. And in this experiment, we made a mixed setup. If we have, for example, 100 pairwise comparisons given, we can use them with this approach, but not with this. This is basically, if we have a label, some classification involved, yeah? For example, an image of a perfect cat and the leg cat. Then we retrieve this image with cat, is preferred over this image with dog. This image with cat is preferred over this image with gorilla. We basically break down the classification data into different levels. Of course, we wouldn't do this in practice. Just to show that it works. Yeah? So in practice, you would already start with preference data because this is the thing you could collect. But this is just meant to show scale. If we use classification data and we retrieve some preferences, then we also perform similarly on the other data. Quite simple, but yeah, this is exactly what we do.
Both of us, yes. Conformal prediction, both of us, yes, all of us conformal prediction is kind of new uncertainty quantification method. Yes. So we need the uncertainty smaller better. So it's represented by rigid lower bound and upper bound. And we need the bound is smaller. And previous work is fixed, and so it's the same for all data. But we use residue to make sure the bound is differently according to how the data looks like. So it's reasonable, right? So it's better than basic baseline model. And besides, we use two separated GNN to train. First is for the prediction, and the second is for the residue. The residue.
Let's say regression.
Yeah, both for regression and classification.
Actually, I come from a different
What kind of data is it?
Most of them are graph. Traffic, election, and others like core or something like that. How about yours?
Mostly horizontally
First is the 贾君腾苏尔超级团体 and another like CF and CG and CGI. You can check it out. Also, I will upload some video on YouTube.
Like showing the results.
Yes, yes. Can you hear me or write my channel? Also, post.
Then the sets are valid. And then the proof is also quite simple because with these properties only, then you can show that there also exists a score. Yeah.
不算特别的晚，22个。对，应该还不
你完整的讲了一遍，这个20-30个完整的讲，把那边分享了一遍。
完整的可能10几个。
太多了，好累。
这挺好，所以到时候你讲的时候可以多准备点，多准备一点吃的。
多准备一点吃的。
你到时候讲的时候啊，我建议你。呀，很累，喝了水。啊。是明天是吧？然后这边其实感觉人没有那边多。好像那里面也是。到温少。Competition is a new method for uncertainty quantification. It's popular nowadays, but there are some questions. For example, nowadays the work. First, we want to learn a region for the uncertainty.
Okay.
Lower bound and upper bound.
Okay.
But nowadays, the previous work usually have the fixed parameter
Okay.
for all data.
Okay.
It's not good.
Okay.
So our work learn according to the data.
Okay.
So learn the residue. Besides, when we learn the residue, we set a separated GN model.
Okay.
Yes, this is so this work well, and there
This is a residual for what?
for
error?
residue for error.
Error in what?
Error between the prediction and the ground truth.
Okay. Okay.
How about
Residual adaptive. Thank you very much.
you can check it out, maybe paper or code, and you can keep my part.
Sure.
I will send some, upload some video on my YouTube channel about pursue PhD or something like that, writing paper, come out idea. Come on, prediction. Come on, prediction. These are
We want to perform a prediction residually weight. Okay, what's the reason? What's the purpose?
the purpose is want to get region. This region means our prediction is highly located in the region. Usually 90%, 95% in this region.
95?
95%.
Yeah, okay, like two sigma.
Yes. But nowadays the model usually have error, big error, because the lower bound and upper bound is not good. Our purpose is to make the upper bound and lower bounds smaller, but at the same time cover 90%, 95% of the prediction. Yes. To do that, we first learn the residue. Is varies according to how data is good. So it's not fixed like a previous work. It's reliable and feasible. It's changeable according to the data. So it's more reasonable and reliable.
So what we have?
We learn two models at the same time. First is for prediction and second for residue. For the error. Use a separate model. Learn the residue. Yes. idea is from intelligent control theory. It's like negative reward in control system, control theory.
We have like another regime. Is it should it be like very light?
Very
The
light.
second way, very light. Light model. Compare this one.
Compare what is lighter. Yeah.
Light, yeah. Because I know, I think previously it could be done even without model, like, but just by just gradient descent or something like that to compute noise. As I understand, you add the model and try to model the noise with the model instead of like just gradient descent. But I am still thinking that it should be very light. You cannot use like very heavy.
Yes. Yes.
Okay, and for the test, yeah, it is understandable. So what's the result? What was the difference?
Results.
First 17.
Yes. First, this coverage is around 95%, and then the interval is much better.
Do you have the noise, the initial noise for this?
Noise, yes. But the noise is generated by by ourselves. It's not generated.
High level is enough. Basically, what they do in the whole prediction is we get a new test instance and then we want to confirm the prediction set. And we want the prediction set to be valid. Yeah? So the certified probability, we want that the true label
What
is
is
set.
Got it.
Okay, so we need three ingredients.
Is ID means test load. Load.
Can we also be regression?
They are around
Why everything is around like minus 0.5?
We need a non-conformity score function.
This have to
This is basically
It's
score the new data points, the hypothetical data point,
reordered
with
and
the score, the
yes.
tells you outconforming and non-conforming. Yeah?
This is meeting and this is the prediction. Prediction. Around 95% is reading.
To tell how non-conforming
95%.
and a very simple example is this lag score, which just uses the counter probability.
Here.
Okay,
So, for example, you get a new data point and you say,
Yes,
okay, let's
yes,
say this is a cat, and it then says this is non-conforming 1 minus the probability that I think this is a cat.
Okay, so let's say we have
5%
predict
is here, and this is there.
0.4,
95% is
then the non-conforming score
in
is 0.6.
0.5
And
interval.
so the
Yes.
the interpretation of the non-conforming score is
I'm
how
wrong.
likely it
I'm
is
wrong.
to be wrong, or how likely it is
This
to
number.
like give you a
Yes,
bad
yes.
set, maybe.
The interpretation would be how
This
conforming is it to
how long
calibration rate.
is this number? And how many is in the
Data generating process,
We can adjust like both. If we choose, if we fix one, the other, like we choose only one. The other is dependent from the second parameter.
Yes. Usually
How do you
control
adjust
this.
the p-value.
But usually done by setting alpha.
So you found both hyperparameters this to be in that way, because if we, for example, choose one, the other can be found. And somehow, but we can interval and we have like bound.
And then you look in your
We look
calibration
at bound
data
and we
where
understand what
The bound is generated by model, not our set. We only set the alpha.
Yeah, I mean,
So you're sort of
okay, I
using
got it.
this is like your decision.
This is
So you choose like about around 95% and look what the number of
So it's 1 plus the sum of if the conformity score.
the length of the
this is the new
interval
data
is.
point.
yes.
the new data point with hypothetical label.
Yep. Oh, so right, so you said you iterate over all the possible labels.
See you later.
So what's the value per label?
Yes. Okay, and for each possible label, you check if it's greater than or equal to alpha. If so, then include it. If not,
like this, you have this validity guarantee. Okay. So this probability is the true one will be inside your head.
对，直播
啊？
可以直播一下。
哦，你在直播？是什么 ？YouTube？
YouTube
可以啊。
对，就是宣传工作嘛。
不错不错不错。这还是要多宣传。
对，多宣传，帮组里多宣传。对。
如果是你们组账号的注册，我也有小红书直播，我跟小红书还更好。
哦，对，手机可能这个，我这个第一次就不太熟，好累。但是我帮你宣传就行。
So you order all the labels, is that right? Yeah. And then you have a new data point.
On the computational machine, and you don't need the value of the score, only the relation is indicated. Only these checks, how many are before, how many are behind. This you can perfectly do with this relation.
Sure.
So given the binary relation of x times y, you can do perform prediction. Just like
So just by using, instead of actually looking at the score, just learning where its relative position is among other like potential labels, you can still do your prediction. And what is complete translated continuously?
complete means that on the whole space x is defined on the whole space x times y.
Okay.
Yeah. Trivial.
Yup.
And it just means
Well, if A is bigger than B and C is bigger than D, then sorry, something like this, something like that.
if A is preferred over B and B is preferred over C,
A is preferred over C. Okay, that's standard, right? I believe that.
exactly. So this is what you need for an odd increment. And it's continuous is basically it's nothing new to say.
It's okay.
It's a little bit technical. You may even leave this out. It still works for both cases. In very synthetically constructed cases like electrographic ordering and so on.
But you need to read it.
Yeah, exactly. Yeah. And then if this holds, then you can the same guarantees as this one. The proof of this scheme is actually quite easy because if this holds, then there's a result from economics which says then there is a real number and you can order on the real number line. So there exists the score. We don't know the score anymore, but it exists. And if it exists, then we have the same guarantee.
Sure, because fundamentally, like here, you just care about who's better than
Exactly, right?
So instead of learning like a score function, which can be really hard and complicated, let's just learn something that gives you a correct order. And then we don't need to be as fine-grained, right?
The typical use case of this is when you have data of this kind. Yeah? So you have data, not with these hard labels, and you say, okay, this image is a dog. But when you have this reference data, this image being a dog is more likely than this image being a cat. And it must not even be the same image. Yeah? Okay, this is more likely to dog than this is a cat.
So instead of like having like an image and a label in your trace data, you have, what do you have? You have like an image and an inverted data.
Like that, yeah. And it could also be two images. It could also be this image being a dog is more likely than this image being a cat. But typically you have the same instance, but it's not restricted to this.
Sure. And this is the last function?
This is the last function we use that's called. So this is what we learned in the Bradley Cherry model. This is already know this is really preference learning. It's also used a lot in this LLM fine tuning and so on. So what it basically does is it learns the utility function, and this utility function is basically ordering the alternatives. And it's a bit more involved than training a standard classifier because it's always in two forward classes. So this is one
what's the like? Why? In what situation would a researcher use preference space instead of vanilla?
You would use it when you have preference data.
Oh, okay. Okay, got you. Okay, okay.
So if you have, for example, if you also have a lot of reference data,
Got
for
you,
example,
got
you use but only a small amount of hard labels, then this will because the hard labels you can also convert to this.
That is true.
You cannot convert this into this.
That is true. So when your data is less certain than having ground truth labels, then with a little more computation cost, you get the same thing.
Exactly. Then you can, if you have only this weak supervision instead of the strong supervision, you can do it.
I see.
Then we did a couple of experiments and it works. It works.
Okay. TLDR experiments work.
This is maybe the most important.
Yes,
Because this is exactly very different. So we have 100 pairwise comparisons, only our values. And then we have standard labels, standard hard labels, in a varying amount. Of course, we start with this advantage here, and then this diminishes as more and more classification data becomes available. And the classification data can be used by our method and the others, but the preference data can only be used by ours.
that's right.
So this is why we have this advantage here, then it diminishes get more
As you have more data, then this guy will perform similarly.
So we never stated